Hello again and welcome to part 6 where we're looking at the Keysight U1282a. Again, this meter was damaged during my transient testing. Doesn't look like we'll be able to repair it. So today we're going to begin our switch life cycle testing. Again, this is going to be 50,000 cycles. And again, to be clear, one cycle will be a complete clockwise and then counterclockwise rotation. That would be one cycle. We've ran this test on a few meters now. The results vary quite a bit. So far I believe the Fluke 17B Plus had the lowest switch noise of all the meters that we looked at. Some of the meters it actually ground holes through the switch contacts. Now again, this is not the first time that we'll be looking at a Keysight meter. I did look at one earlier, but what had happened is I had damaged the circuit board. So this time I decided not to go ahead with further testing of the circuit board to try to see where things had broken down. So you can see there is no damage to the switch contact area at all. Again, this is just magic marker where I traced out part of the circuit board. Again, you can see this board has no sign of grease. I've always ran these tests with the meters unpowered, again because I'm looking at the contact resistance. So the fact that we damaged some of these ICs is not really going to have any effect on this test at all. So one of the problems, of course, is that this meter doesn't fit inside of our test case. This is normally what I'm using to hold the meters when I'm running this test. So I think what I can do is cram this thing in there without the rubber boot. It looks like it just would barely fit. One thing's for sure, once it's in there it's not going to budge. So we don't need our spacer block or anything. And I don't think having the rubber boot on the meter or not is going to have any effect on this test at all. So we'll just be using our two contacts for the power. So we'll be looking across these two sections of the switch. So again, this inside wafer goes to this via here, and then this routes up to at least these two transistors where I've kind of got this marked here in red. Here I'm on one side of the spring, and this would be looking at the one side of this RT6, and here's the other side. You can see we picked up about 1.2 ohms or so. So what I'll be doing is attaching our test wire to this node here, and then the other to this node here where it's in red. So again, this is how we'll be attaching them. Just take a little bit of tape. We'll use this to stabilize our wires, like so. And we'll go ahead and install our two wafers. We'll install our little keypad, and now we can go ahead and install the circuit board. I don't think it's going to matter, but we'll go ahead and put all the hardware back together. So I'm thinking we'll do is just run this cable up the side and then along the fuse, just like so. Yeah, running alongside the fuse, basically this lip here hits the bottom of the circuit board. So I'll run it on the top side of the fuse, like so. That should give us a lot of clearance. Oh yeah, much better, much better. So I've gone ahead and installed our rubber gasket as well as the battery cover. So all the hardware is back together except our fuse cover. And again, no rubber boot. So this is the way we'll run it. We can go ahead and check the resistance real quick. Make sure that our switch is functional. Here it should be an open and the off. We'll be monitoring the resistance using my HB34401A. Alright, let's see if we can just jam this thing in there. Oh yeah, it's tight, but not so tight that it won't fit. That should be a very stable setup. Again, what you don't want is the meter obviously moving around a whole lot. That's a little too tight. That one's pretty good right there. Again, I just use this stepper motor. It's got this fork attached to the end. Again, we have this coupler that allows the fork to float. And then on the end of the fork, we have a couple of pieces of rubber tubing. And this will just fit over the switch like so. This is sloppy as well. Again, we don't want to have any kind of a bind when I run this test. Alright, so here's our setup. Again, we just have the stepper motor mounted in a pan of ice. And we align this thing vertically and horizontally. Again, we don't want a kind of a bind. Looks pretty good. I've got the software all set up. First thing we're going to do is run an alignment. Again, you can see the software slowly ramping up the switch cycle time. Basically what I do is I try to complete all these tests in the same amount of time. And it looks like it's up to speed now. Again, this test will require about 60 hours to complete. Again, the last Keysight meter I looked at, we broke all 4 prongs on the detent spring, and that happened fairly early on. And you can tell when it broke because basically the clicking went away. So pay attention to how loud this meter is, and we'll see how this progresses. Alright, we're about 200 cycles into it already. So far everything's looking good. The resistance is very stable, pretty much what we'd expect. Meter's not going to typically wear out in 200 cycles, I wouldn't think. Alright, we're at about 470 cycles right now. Sounds about the same. Alright, we're about 1,000 cycles into it right now. Alright, so we're about 2,500 cycles into it. You can hear a definite squeak. We're currently at about 4,100 cycles. Okay, we're at 7,800 cycles, and something has just happened with the switch. Okay, we're at 8,000 cycles. I think the meter just jammed up. You can see it's no longer clicking. Oh yeah, some major failure. I mean, there's like no friction whatsoever. Alright, let's see if we can get this back out of here. It's pretty bad that we broke the switch this quickly, but again, the original Keysight meter I looked at, the switch also failed quite prematurely. Oh yeah. So I'm rotating the knob right now, and you can see the switch is not turning. Oh, this is locked up tight. Alright. See that small piece of plastic? It just fell out of the meter. Nice. Alright, let's go ahead and pull the circuit board out. Jeez. That's what's left of the knob. And you can see our seal is still fine. The knob still rotates fine inside of the socket. What we'll have to do is have a look at this under the microscope. This is looking at the software that I use to run the life cycle test. What we can do is just select post process, and we can select add a waveform. And then we'll select the Keysight U1282. This is looking at the raw data off of the meter. The vertical axis is resistance in ohms, and then the horizontal axis is the number of cycles. So again, we aborted this test at a little over 8,000 cycles. You can see at the beginning the meter is less than about 0.4 ohms. You see a little bit of noise. That's not unusual. I've seen that happen, I believe, with other meters as the contacts begin to seat. And then you can see it's quite stable up until we get up to about 7,600, 7,700 or so. That's where there was first signs that something had happened with the switch, where it really started to click really quite loud. And then you can see it stabilizes again. Let's just zoom into this area a little. So you can see we get all the way up to about 10 ohms, and then it settles back down and we go below 0.4 ohms or so, and it's stable again up till the point where the switch again starts to fail. And then of course the shaft breaks, and that's when I abort the test. If we select mean, this is looking at a rolling average of the last 50 cycles, and then this is looking at the accumulated resistance. So basically every time I take a reading, I'm adding the resistance value. Let's just go ahead and we'll load up all the data that I have so far. And again, this is looking at the full 50,000 cycles. You can see I set the limit of my HP bench meter to 1,000 ohms. I'm assuming if a meter reaches 1,000 ohms, it's basically non-functional. So some of the worst meters here, you can see, is this free meter from Harbor Freight. This white one here is our Agilent U1282a. The blue is our Keysight ZT102. Again, a very low-end meter. The green here is probably our UNI-T UT181A+. This large white spike, this is going to be our Keysight U1282a. And again, we only made it to 8,000 cycles with that meter. This gold trace is our EOSUN EM129. The rest of these meters are fairly low by comparison. Let's just go ahead and we'll manually zoom into the vertical. This red trace is going to be Dave's 121GW. See, that takes quite a big chunk out of her. If we zoom in a little further, we're definitely getting down to the better meters. So here, this is the Bryman BM786 in green. Here's the BM839 in blue. Here's the Bryman BM869S in yellow. This purple one here is the Fluke 87V. And this dark blue trace at the bottom, this is the best meter I've seen so far. This is the Fluke 17B Plus. Again, with just a very stable switch contact resistance. Unbelievable. Actually, when we took this thing apart, there's virtually no signs of any wear on the contacts. Very impressive. And again, this is our accumulated resistance. So in some cases, like right here, this is our Keysight meter. Of course, we aborted the test at 8,000 cycles. So you can see it just goes flatline because there is no more resistance to accumulate. Of course, we see the same thing with this trace here. I'm not sure which one that is. Let's see if that's, yep, that's the other Agilent meter. Again, if you could imagine if a meter had perfect resistance, so 0 ohms, and it was able to maintain that for the 50,000 cycles, you would just see a flat line here at 0 all the way across. So the lower that this number is an indication of how good the meters are. And if we have a look at the log, again, the horizontal axis is the deviation from the initial resistance in ohms. So what we would like to see is a switch that basically never changed. And that's what you see up here in purple. This is the Fluke 17B Plus. You can see that it never deviated by even 10 milliohms. So whatever the switch resistance was, which again, it basically starts out at 0.3 ohms or so, and that's saying that the switch never deviated by more than 10 milliohms during the entire duration of the test. Compare that with other ones, you can see like this gold trace here. You can see that that switch is deviated by more than 100 ohms, and it's done it at about 2,000 cycles. So if we have a look at our Keysight meter, we can just change the color of this one temporarily. We'll make it yellow. So again, this one in yellow is our Keysight U1282. The red one is the Agilent U1282a. Let's just go ahead and plot the histograms. So again, the horizontal axis is resistance in ohms versus the number of samples. Let's just set our upper limit for, say, 10 ohms. And we can see for all these meters combined, the majority of the contact resistance is actually well below a half an ohm. All right, so this is looking at the outside case. This is where the detent spring would normally ride. Not a lot of wear, but again, the meter had less than 10,000 cycles on it. So I'm not expecting this to look too bad, or you'd hope it wouldn't. I'm actually surprised it would show any signs of wear at this low of cycles. As you can see, there's a lot of particulates along the edge of this. So some signs of wear, but not too bad. Here we can see one of the cam lobes on the detent spring. Let me just push on this a little bit. You can see there's no signs of any cracking, at least on this prong. Let's have a look at the others. Again, that first Keysight meter I looked at, all 4 of these prongs cracked after just a few thousand cycles. The detent spring on that particular meter looked to be made out of some kind of glass-filled plastic. That doesn't seem to be the case with this one. This is the fourth cam lobe here. Looks good. Again, no signs of any cracking. Next, let's look at the switch contacts themselves. You can see it's starting to wear a flat. You can see it's starting to get a little flat. Let's just see if we can zoom in here a little bit farther. There's definitely some wear on these. Doesn't look like it's cut through yet. Let's have a look at the last set of contacts. And again, definitely some signs of wear. Here we're looking at the top wafer. Here you can see the interlocking tabs. This is where it connects to the lower wafer. A little bit of debris. Let's have a look at these contacts as well. And definitely some signs of wear. Let's look at one of the other ones. It's hard to say. I mean, if we could have ran this thing for the full 50,000, what these would look like. Again, I've seen them where they'll put a little tit like this on them, and after the cycle testing, it'll actually wear right through, and you'll end up with a hole. This is the last set of contacts. Again, it's probably kind of tough to tell on the camera just how much debris is around these, but from my view it looks like there's quite a bit. Let me just try to get it from a side view. We'll zoom in here a little bit further. You can see there's quite a few particulates around this area. Jeez, burn my eyeballs out. Alright. Here we're looking at the back side of the switch. You can see the damage now to the knob. We're missing one of the prongs. I picked up a hair, it looks like. Not surprised, it's been out on the desk for a few days. So the switch had enough drag that it actually broke that plastic. You can see it's still wedged inside of the wafer. This is looking at the circuit board for the U1282a. This is the bottom side, I guess, or the side with the LCD. You can see how the wiper contacts were wearing grooves into these pads. Again, this is only about 8,000 cycles. You can just see those grooves, how deep they are. Be interesting to put this on a profilometer and get an idea of the depth. But you can imagine, as we start digging those grooves in, we're putting a lot of drag on the switch. The deeper they go, the more drag, and eventually it becomes so tight it was enough that it actually broke the knob. Let's look around other parts of the board. Again, you can just see that pattern. I get a little concerned as I start to see copper migrating across the circuit board. Again, if I were to expose the meter to high voltage and we had this starting to bridge the contacts, of course you can imagine that that could cause it to arc over. I don't know if I can tilt the board up on its side, maybe we can get an idea how deep those grooves are. Let's just see here. You can tell they're quite deep. Let's have a look at the other side of the circuit board. You can see there's no pads in this area. Look at how much debris there is though. That black is just where I've marked that via with my magic marker. Just look at all that debris. Again, you can see how deep these grooves are being cut into the pads. And again, this is where all the drag is coming from. I wonder if we could have ran 50,000 if it would actually cut right through the pads. The only reason I aborted the test is, the shaft on the knob broke. There was just no reason to continue at that point. Geez, I wonder, on this pad already, is that cut right through? It almost looks like it might be. What I'm going to do is just take a little bit of Pro Clean on a cotton swab. And let's try to wipe this off just a little bit. This side right here is definitely the worst of the two. A viewer by the name of the HW Cave, they had posted a comment on my last YouTube video that said the one thing I was wondering in watching it is whether the repeated transient test at ever increasing voltages wear out the protection devices. I had a quick look at a little fuse gas discharge tube datasheet, and they do have a limit of how many hits they can handle. Granted, the discharge current in your tests are probably lower than the max stated in the datasheets, but then again, you trigger far many more hits. Any thoughts? It'd be interesting, but probably not practical to do two identical mock-up protection circuits and test one like you did for the U1282a multiple times with ever-increasing peak voltages until it fails, and a second one with just the transient that caused the fail in the first one. So let's just look at a couple of data sheets from DigiKey's website. This part is made by Little Fuse. In the center here we can see the IEC current pulse. So this is an 8 microsecond rise, 20 microsecond full width half height current pulse. With a 10 kiloamp peak, it can sustain 10 shots or 10 transients, but at 5 kiloamps it's only rated for one shot. If we look at a Born's part, again we can see at 3 kiloamps, 8 microsecond rise, 20 microsecond full width half height, one operation. With a 2000 amp peak with the same rise time and full width half height, it's rated for 10 operations. Again, looking at our Keysight meter, here's our input. Again, this goes through a PTC. That PTC measures 700 ohms. That's in series with this resistor. That resistor has a value of 250 ohms. And there's two of these circuits in parallel. There's the second PTC and the second resistor here. Backside of these, we have our two gas discharge tubes, and these go back to the common point. So this is essentially our circuit. So let's just say we were going to hit this thing with a 6 kV transient. So if we look again at the circuit board, these are marked 2000, so I believe these are probably breaking down at somewhere around 2 kV. So we're going to subtract off the 2 kV, and we have a total resistance of 950 ohms. So this gives us a peak current of 4.2 amps. Okay, so in the data sheets again, they're talking about 1,000 to 3,000 amps. In the multimeter, because these are sitting behind these two devices, it limits the current. So what I'm suggesting is that in cases where we have a multimeter, the GDTs are probably not going to see any kind of wear. And I've said that about the MOVs as well, again, because people have voiced their concerns over those failing long term as well. I have yet to see a MOV fail out of all the testing that I've done. I've never seen one leak, never seen one crack. What I have seen fail is when the companies will use the 5mm PTCs. I've seen those things actually blow apart. Same thing with the surge rated resistors. I think I've had one or two of those fail. Typically what happens is downstream from here we've got a clamp circuit, and those clamps are typically what get damaged. So again, these aren't active all the time. These are going to be in series with the function switch. But I have seen these come apart. Normally what ends up happening is they have enough to limit the current before it gets into whatever ICs, so these will fail short and they save the circuit downstream of it. Of course, that's not what's happened with this meter. We've damaged quite a few of the ICs on this board. So again, the question is, if we were to apply several transients to the front end of this meter, and we'll just leave the switches in the off position here, so we're guaranteeing that we're exercising these gas discharge tubes. And what we do is we measure the breakdown voltage before we do any kind of transients. And then what we'll do is we'll set up the transient generator where it just continuously fires into this circuit. And then after some time, we'll go back and we'll measure the breakdown voltage and we'll see if it's changed at all. In order to measure the breakdown voltage, we're going to be using our ESD gun. Again, this can output a DC voltage. And then this meter again in the upper right gives us a rough idea what the output voltage is. Again, we're just going to attach this right to the inputs of the multimeter. And you can see we have our function switch set to the off position. And let's go ahead and start turning up the voltage. And we'll see where this thing folds back at. So again, this is in kilovolts, so that's roughly 600 volts. Here's 1000 volts. So that's pretty close to the limit right there. So you can try just squeezing a little bit more out of it. Right there. I'm going to say that these break down at 1.89 kilovolts DC. Now what we're going to do is set up our transient generator. So in the upper right you can see I have my original transient generator out. This is attached to these two leads, and currently I don't have them connected to anything except our high voltage probe. Again, that's going off to our oscilloscope, and this is currently set for 2000 volts per division. You can see we're roughly 2.5 divisions up, or roughly 5000 volts peak. Again, this transient generator has a full width half height of 50 microseconds. And the scope is currently set for 50 microseconds per division. So if we go up halfway, you can see we're roughly 1 division over. So a 50 microsecond full width half height. Again, it also has a 2 ohm source impedance. So this old transient generator can output 14 transients in 30 seconds. So if we wanted to run up to 1000 transients, it's going to require roughly 35.7 minutes. Alright, so we'll just be attaching our transient generator again right to the input of the meter, like so. And I'm going to elevate it above the table with a block of wood. And here you can watch it with the clock. And I think we're good to go. We'll just let it run. You can see the gas discharge tubes firing. I'll turn off the light. Again, this transient generator can only put out about 20 joules. Batteries died in the camera. So what are we up to? Looks like 5 minutes too. So I think we've been running about a half an hour now. I'll just let it continue to run. Again, we can see the gas discharge tubes are still firing. There you go. Alright, so it's been running for roughly an hour now. So certainly well over 1,000 transients. We'll go ahead and turn it off. And let's go ahead and disconnect it. And I'll get my other transient generator out. And we'll just attach this to the front end of the meter like before. We'll leave it set up on this block of wood to isolate it from the table. Right there. So about 1,800 volts, which again, that's right in the ballpark of what we had the last time we measured it. So yeah, again, after about 2,000 transients, it doesn't appear that we've changed the characteristics of the gas discharge tubes at all. But again, we're only talking, even if I was applying 6,000 volts, we're talking about roughly 4.2 amps is all across the gas discharge tubes. So the wear factor is going to be much higher than what it would be if we were pumping 2,000 amps through it or so. Well, I think that's going to conclude my review for the Keysight U1282a. For the viewers that took the time to vote for this particular meter, I hope you found the video useful. To summarize my thoughts about this meter, again, we're looking at about $650 or so for this. So it's a fairly high cost meter. Right off the bat, I wasn't impressed when I saw in the specifications that they had rated this meter to 100 megahertz, where its upper end was basically 30 megahertz. Again, I could care less if a meter could read 100 megahertz or 30 megahertz. I'm going to use a frequency counter or a scope if I'm looking at higher frequency signals. It's the fact that Keysight would feel the need to overspecify what the meter is capable of. Again, I had demonstrated a SEM meter, and that particular meter had basically the same specifications of this Keysight, but I demonstrated where that SEM meter could read up to 120 megahertz. In previous videos, I've shown it all the way up to 150, and that meter is still quite accurate. This meter just flat out can't read. Next, I was disappointed that the lettering was etched from my chemical test. I mean, you can just see that it rubbed it right off. Again, that's not something that we normally see when I run that chemical test. Real cheap meters like the Annex, I've seen it actually melt the display. And I think on Dave's 121GW, it was stripping the lettering like this Keysight. I would think if companies like Bryman, Keysight, Fluke have the lettering sorted out, Keysight would have too. And of course, the fact that the meter was damaged with a 5,000 volt transient, I'm totally unimpressed. Again, our runner-up in my original $50 meter shootout was that Amprobe AM510, and that was damaged at 5.8 kilovolts. Seeing this meter get damaged at 5 kV, just like the previous Keysight meter I looked at, it just doesn't set well with me. And even worse is the fact that the meter was damaged beyond repair. Again, that Amprobe meter at $50 and a lot of the other meters that I've looked at, even if I damage the meter, it's typically going to be something in that high-speed clamp circuitry. Maybe you'll blow open a resistor or something, but that's usually about it. It's rare that on these higher-end meters you'll actually take out the main controller IC like what's happened with this one. It looks like with these, whatever happens, that transient blows through, maybe gets onto the logic supply, because we saw two of the logic controllers plus that main controller is out, and it looks like the RMS to DC converter is out. So whatever they've done to try to protect this meter, it's not adequate to actually protect the ICs. So if this thing gets hit, it's going into the dumpster. Other meters that I've damaged, even the Brymans, the Yokogawa for example, I've been able to repair just like that cheap Amprobe meter I tested. So unfortunately for this meter, unless I could actually get parts for it, there's nothing I can do with it other than recycle it. And of course, we also tried data logging with the meter, and we found another problem with it that other owners of the meter were able to reproduce, where the meter will glitch. Now, I went so far as to write my own software. I removed their cable from the equation by using another cable that I had, and it still glitches. So I believe whatever the problem is, it's in the firmware of the meter. You could probably write custom software to work around the problem. But again, why? The meter should work. And of course, then we have this life cycle test. Again, this Bryman BM869S, this has actually been through the 50,000 cycle test. I still continue to use it. Again, I also ran a Bryman BM789 through the same 50,000 cycles. And both of those meters continue to work just fine. So overall, I'm just not very impressed with the meter, especially for the high cost. It's been very disappointing. Well, I think that's going to be it for now. Hopefully you enjoyed the video. I don't know when I'll be looking at another handheld meter, but if I do, we'll see you then. Later.